Hello friends, in this lecture I would like to explain another example based on the rectangular beam which was continuous beam. So already in the previous lectures I explained singly reinforced sections, that is singly reinforced rectangular beams, doubly reinforced rectangular beams, and again flanged beams which is T beam, and also cantilever beam. So in this lecture I will explain continuous beam here. So see the given data. Design a continuous RC rectangular beam. Number of spans will be 3. Clear distance between the supports will be equal to 3600 mm, and width of the supports, means the column supports, will be given as 300 mm. Imposed load not fixed, imposed load fixed. So generally the data will be given in terms of live load like that, but while calculation of the continuous beams the data will be given like this: imposed load not fixed, imposed load fixed. Why? Because for calculation of this type of continuous beams, see here, bending moment coefficient for continuous beams and slabs, generally it will be given in terms of dead load and imposed load fixed, imposed load not fixed, like that. Therefore the given data for continuous beams also in that way only. And for this data you have to design the continuous beam. Okay, see here, given number of spans will be around 3, so I will take that point here. So these are the width of the supports. So I will just show some rough diagram. Number of spans will be around 3, like that. So what is the given data here? So number of spans, like 1 span, 2 second span, 3. So this is the span which we are designing here, and clear distance between the support. We know the clear distance between the supports will be equal to 3600 mm, and the width of the supports will be given 300 mm. Similarly this one also 300 mm, 300 mm, 3600 mm. So this is the given data. Then what is our first step? So our first step, each and every time along with the given data we have to design for M20 grade concrete and Fe415 steel. Okay, so our first step is choose the suitable effective depth and overall depth for the beam. For that you can take span to depth ratio, that is L by D ratio. So we know that L by D ratio which is does not less than 26 for the continuous beams. So we can select the range will be less than 26 only. Here I will take L by D ratio will be 15. So what is your L? L is the clear distance between the support. Therefore I will take cross multiply here. L by 15 equal to D. What is L here? L will be given 3600 mm, and I will select with 15 range. So around you will get, if you simplify this one will be around 240 in mm. So effective depth will be around 240 mm. Therefore approximately I will take 250 mm for my design purpose, and overall depth will be around 300 mm. Okay, so if you want you can choose this effective depth 240 and overall depth 300. Here the effective cover will be approximately 50. Here if I choose 250 and 300, if you choose this 240 default like that only, and choose overall D will be around some 300, means their effective cover will be around 60 mm. So it is your wish, and you can check the whatever the depth you are taken, it will meets the required criteria or not. So I will show that point also. Then after choosing this one, and again assume width will be equal to around some 230 mm. If you, so here I am taking width will be less than this effective depth, otherwise you can take 250 also, no problem, but both ranges will be equal at that time. It will be comes under some more or less equal to square, but D will be higher only, no problem. So choose effective width whatever you want. So the width of the beam 250, 240, 230, whatever you want. Then your next step is effective span. So generally in the, so which is effective span here? So generally for simply supported beams, what is the procedure for calculating effective depth? So that is center to center of the supports, center to center of the supports, and second one is clear span plus effective depth. So this is for simply supported beams. But for continuous beam, what is the condition? You once check in the code book, which was in page number 33. So this is page number 33. So if you read continuous beam or slab, in the case of continuous beam or slab, if the width of the support is less than 1 by 12 of the clear span. Here, if the width of the support is less than 1 by 12 means L by 12. So width of the support is given as 300. Check here. L will be 3600 according to our question. How many times? 12, 3 times. Means if the width of the support will be less than, here it will be equal. Both will be equal. 300 and 300 will be equal here. But what is the condition here? If the width of the support will be less than 1 by 12 of the clear span, the effective span shall be as 22.2.A. 22.2.A means this is 22.2 and this is A. So if it will be less than L by 2, you can take down the effective span as like simply supported beam. What I explained now, clear spans plus effective depth and center to center of the supports, take whichever is less. But here it is equal. At that condition, what you have to choose, and if the supports are wider than L by 12 of the clear span or 600 mm, whichever is less, the effective span shall be taken based on these conditions. So at that time, if you choose this condition, the effective span shall be the clear span between the supports. So whatever the clear span you are getting, the same one you are taking effective spans. Here effective span will be clear span only, okay, which is clear span. But if you are getting the point, if it will be L, BW will be less than 12. For example, it will be 300 means your width of the support will be around some 280. At that time you can choose simply support like as simply supported beam. But here both are equal, therefore we are choosing like as the first condition. Center to center of the supports, sorry, clear span is the effective span according to our condition. Then next step is check with the loads. Loads. Here loads. So first point is, here in the code book, clearly observe what is there in the code book. Here dead load and imposed load. Okay. And imposed load not fixed. Dead load and imposed load fixed, imposed load not fixed. So here I will write both the conditions. Dead load and imposed load fixed. That is one condition. And again imposed load fixed, and that is another condition what is given in the code book. And see the data in the question. Imposed load not fixed is 5 kilonewton per meter square. So imposed load not fixed. So imposed load, here this one will be imposed load not fixed. So this is not fixed. But in the question given, imposed load not fixed will be equal to 5 kilonewton per meter square. And another one will be imposed load fixed is 7.5 kilonewton per meter square. So given imposed load fixed, only imposed load fixed is 7.5 kilonewton per meter square. So take down this line like that only continuously. So see here one data will be given imposed load not fixed is 5 kilonewton per meter square. So in the code book the direct value will be there, imposed load not fixed. And again one more data according to the code book. According to the code book the data will be dead load and imposed load fixed, but in the question they will give an imposed load fixed, but here dead load is lagging in the question, therefore we can take dead load also. Okay, for taking the dead load we know the condition, dead load is the self weight which is b into d into 1 for 1 unit meter into unit weight of RCC. Okay, we know this condition already, we solved previous problem like this only. So what is b? They will give, we are choosing that one will be equal to 0.23, and d will be the depth, how much we are taken. Here we are taken approximately 300 mm, which is 0.3 in terms of meter into for 1 meter into unit weight of RCC. So it will be in terms of kilonewton per meter cube. All these are in the meters, so meter cube will be cancelled. So overall the value obtained will be kilonewton per meter. If you simplify, how much you will get? You will get around 1.725 kilonewton per meter. So if you understand the logic here, in the code book there will be dead and imposed load. Okay, if you add both these two, you will get dead and imposed load only. So therefore I am adding 7.5 and 1.75. So that is both dead load and imposed load, which is fixed. So how much you will get? 7.5 plus 1.725. So if you add around, you will get 5 to 7, around 9.225 kilonewton per meter. Okay, and imposed load is fixed, will be 5 kilonewton per meter square as usual, like that only. But in the data they will given dead load and imposed load directly, means you no need to calculate like this again in the self weight of the structure, but they will given only imposed load. So we have to add dead load also for that one. So after obtaining this dead load, so generally this dead load will be only dead load, that is not factor load. Again you can make this factored dead load and imposed load fixed as factored load. So that is we are making this one into factored load, which is WUD, again 1.5 times of 9.225. It will be around, you will get 13.84 kilonewton per meter. Again for this imposed load also you will make this into factor, which is 1.5 times of this 5 kilonewton per meter. So this is kilonewton per meter only. So here if you simplify, how much you will get? You will get around 0.5 times extra, that is 7.5 kilonewton per meter. So this is the way how to calculate dead loads and live loads individually. First see the given data, based on that only according to the code you can adjust your loads, dead load and live load. Then so this is your dead load and this is your live load. Then move to the next point, that is already we know after obtaining all these things, our next point is calculation of the moments. Generally what we take for the moments for general beams? For general beams we take the formula mu equal to 0.138 FCK BD square into D minus 0.42. Some value will be taken according to the code book, but here bending moments will be taken as per the code which is given in the IS 456. See here bending moment coefficient for the continuous beams. For the continuous beams, write down table number 21, page number 36. So this is the code what we have to refer here, and here calculate the span moments and calculate the support moments. See here each and everything we have to find out. Okay, first I will come from one by one. Here the range will be 1 by 12 to 1 by 10. So this is dead load, we know that WUD, and this is live load, we know that WL. So factored live load, factored dead load. So we can add both of these things. Again here also WU plus WUL. Here WUD plus WUL. Here WUD plus WL. So like this we have to take down the values. So these are the coefficients what they are given. See here I will take according to the load 1 by 12 to 1 by 10, first one, which is near end of end span, near middle of end span. Okay, at the middle of end span or near middle of end span. So write down the heading as it is, near middle of end span. So here take down near middle of end span. Near middle of end span. So what are the conditions? So here WUD, WUL. So 1 by 12 WUD L square plus 1 by 10 WUL L square. So generally for simply supported beam, maximum moment will be WL square by 8. But here for continuous beam, you can take WL square to the given coefficient. So this is the formula what you have to remember here. And 1 by 12, what is WUD? WUD will be, which is imposed load is, factor load is fixed, that is 13.84 into effective length will be 3.6 whole square plus 1 by 10, 7.5 into 3.6 whole square. If you simplify this one, how much you will get? You will get around 24.67 kilonewton meter. So these are the positive moments. Okay, these are the positive moments. And again, next step in the moments itself, you can calculate. Next step is the at middle of interior span, at middle of interior span. So the range will be, how much it will be? 1 by 60 into 1 by 12. So here 1 by 60 into 1 by 12. So 1 by 16 W U D L E square. This is W U L L E square. And again 1 by 16 W U D will be same values, 13.84 into effective span whole square plus 1 by 12, 7.5 into 3.6 whole square. If you simplify, how much you will get? You will get this one will be around 19.31 kilonewton meter. So this is another range. You please keep this both positive movements one side. So these two are the positive moments. And again come to the next condition, which is this one, support moments. So take down the heading support moments. Support moments. And again in the support moments, what are the headings? At support next to end supports, at support next to end supports. So what are the ranges here? Ranges will be 1 by 10 to 1 by 9. The ranges will be 1 by 10 to minus 1 by 10 to minus 1 by 9. And again same conditions, that is WUD LE square, WUL LE square. Again simplify these two, minus 1 by 10, WUD will be 13.84, effective span will be 3.6 whole square. Again take down minus common and you can take both these values. You will get again minus 1 by 9, WUL will be 7.5 into LE square will be 3.6 whole square. You can take down, if you simplify these two, you will get a negative, maximum negative moment will be 28.74 kilonewton meter. And again next condition will be at other interior supports, at other interior supports. So this is one condition, the support moments. So what is the range here? Again 1 by 12 to 1 by 19, that is minus 1 by 12 to minus 1 by 9. Okay, and again this is in the range of WUD L square means what is WUD? 13.8 into L square will be 3.6 whole square minus WUL means 7.5 into 3.6 whole square. Again if you simplify you will get around 25.7 kilonewton meter range. Okay, approximately I am taking. If you see here, you observe, you will get negative moments to one will be 28.74, another one will be 25.7, and positive moments will be one will be 24.6 and another will be 19.31. So what is the condition means there will be four moments. There will be four moments on a beam. So moment one will be positive moments will be 24.6 kilonewton meter and another one will be 19.31 kilonewton meter at the span moments, and at the support moments one will be negative 28.74 kilonewton meter and negative another one will be minus 25.7 kilonewton meter. So generally what is the procedure means for each and every moment you have to find out the area of the steel and provide for the area of the reinforcement for particular moment. But here what I am taking means I am taking what is the maximum moment, means if I am providing area of the steel for the maximum bending moment means automatically it will be restricted to the minimum also. For example, if I will take down this moment and I will find area of the steel means, but this is the maximum bending moment comparing to this one, so at that time this is the failure condition if I will provide area of the steel for this one. So general condition means you have to find area of the steel for particular moment for each and every support for the middle of the end span and interior span, and again for the supports which are in the next to the end supports and interior supports. Like that for each and every moment you have to provide the area of the steel and then you can provide individual area of the steel whatever obtained here. But what I am doing means, so in the span moments I will take higher moment and for that higher moment I will provide area of the steel, and again in the interior support I will take higher moment and again I will provide area of the steel for that higher moment only. So what is the rule here means if I will provide higher bending moment area of the steel for the higher bending moment means I will restrict that higher bending moment through the area of the steel. So automatically it will be restricted for the smaller moment also. If you provide smaller moment to the area of the steel, automatically it will fails when higher moments will be applied. So that is the condition here, what you have to remember. Then in the support moments, you see before going to the reinforcement, you first check the depth required. Depth required. So already I told you I will adopt the depth will be around smaller depth will be around 250 mm. So you can confirm whether it will be correct or not. So mu will be equal to 0.138 FCK BD square as per FE 415 condition. Then what is your mu? So in the entire moments what obtained here, in the entire moments already for me it will be obtained higher moment will be 28. So I will take higher moment will be 20. Okay, whether in the tension side or support or span moments. So I will check with the higher moment whether it will support or not. So I will take around 28.74 in terms of mm, that is 10 to the power of 6, and all the values here it will be Newton means you can convert into Newton whatever the value obtained in kilonewton. So 0.138 FCK will be around 20 given M20 grade concrete, and B will be width of the beam we are taking 230 mm, and D square. So check the D square. D is your unknown here. If you simplify, your D will be around 213 mm. See, minimum depth required will be here, the minimum depth we are checking with minimum depth. Minimum depth required for this particular beam will be 213 mm, but we provided 250 mm. So we are in safe side, no need to bother. For example, if you prefer D will be equal to around 150 or 200 mm, definitely we have to change this D minimum restricted to 213 mm. At that time approximately we have to provide 220 mm. Again we have to redesign this one. Here already we are in safe side only. Then go to the next point, which is providing reinforcement at supports. Reinforcement. Reinforcement at supports. So as for the same formula which was in Annexure 96, take down the same formula. So we solved so many problems through this formula. So I will show once again here. It is always better to remember the formulas directly. See here, this is the formula which was in the code book, page number 96. M equal to 0.87 Fi AST D into 1 minus Fi AST BD into FCK. So take down that formula directly. Mu will be equal to 0.87 Fi area of the steel D into 1 minus Fi AST by FCK B into D. So already we people know reinforcement at support what I told. I will take higher moment at support what we obtained. One will be 28, another will be 25. So I will take 28 here into 10 to the power of 6, 0.87, and again the steel will be 415 and area of the steel is the unknown here. D will be 150 minus 1 minus Fy will be again 415, area of the steel is your unknown, and FCK will be 20, B will be 230 and D will be 250. So if you simplify, you will get in the calci directly through quadratic equation. So if you simplify directly, the value obtained will be around 367 mm square. So this is the area of the steel obtained through the particular moment, which is 28.7. Then check with the number of bars. Number of bars will be equal to approximately capital AST by small AST. Capital AST will be 367 only. Small AST will be checked with pi d square by 4. So I will choose the diameter for my trial will be 12 approximately. So already I solved so many problems coming from 10 dia, 12 dia, 16 dia, 20 dia. But we will restrict the formula. We will make the problem somewhat in less time only. So already I solved this number of bars so many times. Okay. So I am checking with the 12 dia bar. So how much you will get if you check with the 12 dia bar, you will get pi d whole square by 4. Approximately the value will be around 3.24. Means if you will get 3.24, it is not possible to keep 3.24 like that only. Go to the next number, which is 4, and check the overall area of the steel, how much obtained if you keep 4 bars. That is 4 into pi 12 square by 4. Why? Because we chosen 12 bar. If you check with this condition, your area of the steel will be around 452.16 mm square. See here friends, already your area of the steel will be 367. The obtained value here will be around 452. So area of the steel required will be lesser than the area of the steel we are going to provide. So this is the provided value. So it is in safe side only. Therefore, I will go with this value without any another try. Okay. And one more thing, what I am telling means, so again at the support there will be one more moment, which is mu will be equal to 25.7 kilonewton meter. If I check with this condition, what happens? Your area of the steel will be lesser, which is lesser than 367 mm square. And again if you confirm with the area of the bars, maybe you will get 12 dia bars only, but it is not that much lesser, which is very near. Maybe you will get 12 dia bars, maybe some 3 in numbers. Therefore what I am telling means, check the higher moment at the supports and you can provide both the reinforcement to the lesser moment where it will be available also. Don't check each and every time all the moments. Okay, if you want economical calculations, you can check with this particular value and you can provide the suitable value also, no problem. Okay, then I will go to the next one, which is reinforcement at the middle spans. So reinforcement at the mid spans. Reinforcement at mid spans. So what is the moment higher at the mid spans? One moment will be obtained will be 24, another will be 19.31. So I will check with this 24 moment only. So write down the same formula, that is the area of the steel, which was in annexure 96, page number 96, area of the steel FCK BD. So which is the moment will be higher, again I am taking 24.67, 20 to the power of 6, and simplify the value here. So the formula will be same. Area of the steel is unknown, 250, 1 minus Fy will be 415. So I am writing each and every time the formula for better simplification. 230 into 250. So if you simplify, your area of the steel will be around 307.4 mm square. I will tell you one more condition here. So already we provided one area of the steel in the for this moment. This is around 12 bars of 4 numbers. So which is 367 mm square. Here the moment will be 307. So the same area I will provide here. Here how many bars we are provided? Here we provided 4 bars of 12 dia. So area of the steel provided will be equal to 452.16 mm square. But here if you provide the same bars for this moment also, okay, no problem. For example, here area of the steel will be 307. Already we provided for moment 397, 367, which was 4 bars of 12 dia. If you want again economical calculation, you can check like this, what I told before. So that is 307.4. Again check with the same dia bar. Pi d square by 4. How much you will get? You will get around some 2.91. So here if you get this calculation, one bar will be decreased, which is approximately 3. Check with the same bar, which is 3 into pi 12 square by 4. So it will be around how much you will get? 339.3 mm square. Means comparing with this previous one, for this one you can select this one, means it will be one bar will be reduced. But in the entire span you can select the higher moment, and for that you have to provide entire beam also sufficient only. So here we are providing 3 bars of 12 dia. So area of the steel provided will be 339.3 mm square. Without calculating this one, for this moment you can opt previous one also, okay, 4 bars of 12 dia, area of the steel will be 450 also, no problem. Okay, then after obtaining this one, your next step is providing shear reinforcement. So we know the condition for providing shear reinforcement. So how to provide the shear reinforcement? First calculate V value, which is Pu by Bd. So and again for Vu, so generally for simply supported beam, Vu will be calculated WL by 2. But here for Vu also there will be standard coefficients. See in the page number again 34. So we are in which page number? So see here, for shear coefficients, maximum shear force at the support next to the end supports, means you have to check the shear supports for each and every value. But where is the maximum shear force coefficient, which is 0.6, 0.6. Here I will take that value directly, outer side, inner side. You can check with all the values, and you have to provide higher shear coefficient, which one obtained here. So I will go with the direct value, that is 0.6 times of W into L. This is 0.6 times of WD. into L. This is WL. So we know the condition. So I will directly here. VU will be equal to W 0.6 W U D into L plus 0.6 WUL into L. So if you simplify this one according to the shear coefficient, how much you will get? That is 13.84 into length of this span will be around 3.6 plus 0.6 around 13.84 into length of this span is 3.6. So if you simplify, you will get 46.1 kilonewton. Like that, you have to check each and every coefficient, and again in that you can provide maximum for maximum shear support only. You can check the tau value. Okay. So I will check with the this value 46.1 kilonewton into 10 to the power of 3. We will get value in Newton, divided by B value will be 230, D value will be 250. So this is the same procedure. Already we calculated so many problems by this procedure. So which is Newton per mm square. Then tau c. So for calculation of the tau c, we require percentage of steel. So we know that was in next page. So generally that page number will be 73. So each and every you have to check with the code pages. It is not possible to remember all the formulas. So with the page number 73, design strength of the concrete, which is 100 AST by BD. So first calculate that one 100 area of the steel by 2D. Again you will get one confusion here, how much area of the steel we have to provide. So one will be chosen 4 bars of 12 dia, another will be chosen 3 bars of 12 dia. Always take an higher area of the steel. You can check the higher area of the steel. It will be sufficient for all the other reinforcement also. So therefore 100 area of the steel will be 452.4 by B into D will be 230 by 250. So it will be around 0.87 percentage. So I told you so many times how to interpolate these values for percentage of steel. It will be 0.787, means for M20 grade concrete 0.787 lies in, where it will lies, it will lies between 0.75 and 1. So you can interpolate with this 0.5 to M20, 0.56 to 0.62. So whatever the value obtained, it will be between 0.75 and 1 only. Okay, maybe you will get 0.56, 0.57, 0.58, 0.59, 0.60, 0.61, 0.62. So whatever the value, so the tau c value lies will be between 0.56 and 0.67. So don't take approximate value. I showed so many times how to solve this procedure for the previous 4 beams. You please check the procedure how to calculate the interpolation and then take down the value. So I will take the value of 0.57. Why? Because already I showed you how to calculate this model. Maybe approximately you will get some other value 0.58 also, no problem. But don't take direct value. You can interpolate this one once. See here, tau v greater than tau c, that is 0.80 to 0.57. You please remember one more things here. The tau v range will be after calculation of the percentage of steel. So it will lies between 0.75 to 1. So the range will be 0.56 to 0.62. So if you observe clearly, so your tau v range will be some 0.61, and you can we don't know tau c at that time. If you calculate means you will get 0.662, we will get confused. but already tau v value will be higher. Already if you take 0.62 also, it will be higher. So at that time you don't waste for calculations. Why? Because you can take down any one value which is intermediate value. Why? Because your tau v range is more higher, even though it will be higher than 0.62. So then you can take any value also, no problem. Okay, then so here your condition tau v greater than tau c, and check with tau c maximum. Tau c maximum will be for M20 grade concrete, how much it will be? So which was in the next table, it will be around 2.8 kilonewton, 2.8, and design stress will be given in terms of Newton per mm square. So tau v will be 2.8 Newton per mm square. See the condition, tau v greater than tau c and less than tau c maximum. Okay, so this is the condition lies. If tau v less than tau c, you can provide minimum shear reinforcement. Already I solved that models. If tau v greater than tau c and less than tau c maximum, you can solve reinforcement based on the IS 456. Already I solved this type of model for the doubly reinforced section in our problems. And if tau v greater than tau c and greater than tau c maximum means, then you can go for redesign. Maximum that type of conditions are not obtained. If you will get means, you can go for redesign. Okay, so I will provide the shear reinforcement according to the IS 456. See here, according to the IS 456, so take down this formula as it is, and again VUS equal to this value, down one by one. So for providing shear reinforcement, the formula will be VUS will be equal to 0.87 F5 ASV D by SV. So here your SVV is the spacing of the stirrups, and again 0.87 F5 ASV D by VUS. What is VUS? VUS again in the code book formula VU minus tau C into BD. See here the value will be VU minus tau C into BD. And again, what is VU? We know 46.1 minus tau C value will be obtained value 0.57, B value will be around 20, which is 230, and D value will be 250. If you want in terms of meters, you can take 0.13 like that, 0.23, 0.25 like that. So take down all the values. Your obtained value will be directly 13.225 kilonewton. Then here you please substitute this value here, that is 0.87, Fi will be 415, and again for ASV, so here I am choosing 6 diabars, 2 legged, means 2 legged 6 bars, 2 into 5 6 square by 4, so that is 2 legged 6 mm diabars. So if you simplify, you will get this one will be 56.55. So here I will get 56.55 in the place of ASV. D will be 250. So I told you what is two-legged, how you can calculate all these things in the previous problems itself. So entire procedure remains same. So no need to calculate each and every time again and again. So just to check what I told in the previous problems, and if you simplify, your SV will be around 230.8 mm. So after obtaining this one, again check with two conditions, which is 0.75D, that is 0.75D will be 0.75 into 250, it will be approximately 187.5 mm, and the next condition is does not greater than 300 mm. So out of these three you can choose whichever is less. So the lesser value will be 230. So I will keep 230 mm spacing. So provide two-legged 6 mm stirrups at a spacing of 230 mm center to center throughout. Okay. Sorry, I am not checking with this one. So your lesser value will be 187. Therefore, provide two-legged 6 mm stirrups at a spacing of 187 mm center to center. It is not possible to keep 187. So therefore, take down base value 180 or 185 mm center to center like that. Okay. Then go for the next step, deflection. Check for the deflection. So how to check the deflection? Already I told you the formula. What is the formula? L by D provided less than L by D maximum. So what is this L by D maximum? That is L by D basic into KT. I am not taking KC and KF because this is singly reinforcement section, only you will get tension reinforcement. And again KC and KF will be, there will be no flanged beams, therefore we are omitting KF. There will be no compression reinforcement, therefore we are omitting KC also. So what is the L by D basic range? That is 1 by 26 for the 1 by 26 for the simply supported beams. Your L by D basic will be 26. Sorry, 1 by 20, not 1 by 26. L by D basic does not less than 26 means 26 for the continuous beams. For simply supported it will be less than 20, and for cantilever we are taking around some 7. And how you can calculate this KT? So already shown you so many problems how to calculate this tension reinforcement, which is number 30. See here page number 38. So for calculation of the tension reinforcement, so 0.58 15 area of the steel required. How much you have to take? Area of the steel required will be around 307.4 and provided will be 339. So I am checking with one condition, which was the movement of the spans in the middle spans. So reinforcement at mid spans I am checking here. Okay. And for that how much you will get? The curve will be around 280 Newton per square. Sorry, the curve range will be 218 Newton per mm square. And the 218 will be lies between here, like that it will goes like that it will. And we know how we, what is tau c value here. So percentage of steel will be calculated here of by BD. So for obtaining this value, area of this will be 307. Here I use into D will be 230 into 250. So how much it will be? It will be around 0.59. Check here, 0.4 to 0.6 somewhere here. So percentage of reinforcement 0.6 approximate value, nearer value. So I will check with this line and I will choose to the part here 1.2 1.4, between I will take 1.3. So your KT value will be 1.3 approximately. Like that you can choose the range. Already these models I will explain previous problems also. So this is 33.8, but check with the L by D what you provided. L will be 3600, D will be 250 you provided. So it will be 14.4 and it will be 33.8. So L by D provided will be lesser than the L by D maximum. So what are the maximum to the particular problem? So we are in safe side. Therefore, your check for deflection also safe inside. So check for deflection is safe. Okay. So this is the way we have to provide the, you have to check the deflection. After that, you have to provide the reinforcement at mid spans and interior spans. I will explain that also. See here how you have to provide the reinforcement. So I will take the continuous beam along with the supports. First support, second support. Approximately I will take this one with some range. Third. So number of span will be minimum 3. So I will take minimum 3. Up to here only it will be enough. Okay. Then here we know the condition, one condition. What is one condition? For the, there will be 3 bars of 12 diameters at the mid span and 4 bars of 12 diameters at the supports. Okay. Here we know one condition. For resisting of any beam, minimum 4 bars will be required. Minimum 4 bars will be required. Minimum 4 bars will be required. Okay. I will stretch these bars. For example, if I will cut the cross section, then only it will be visible. Okay. So if you will expand these bars, there will be 2 bars aside. So if you see from side view, you will visible only 1 bar. So both this bar, one will be here, and again if you stretch this bar, another will be other side, and again here also one will be this bar, another one will be this bar, like this. If I am seeing side view, it will be appearing like this. So here I keep 2 bars of 12 dia upper side, 2 bars of 12 dia, and again in the bottom side also 2 bars of 12 dia. But according to our condition, what is the mid-span range? For mid-span, it required minimum 3 bars. 4 bars of 12 mm diameter at the supports. Where you will get support? Supports will get here, this position. Here. Here like this. So these are the supports. And what are the middle spans? Here. 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 So for middle span, minimum 3 bars will be required. For supports, 4 bars will be required. Means I will provide that also here with the green bars. So I will choose. I will keep one more bar here. So 2 bars. I will stretch a side by side here. 2 bars I will keep in the same line. Automatically it cannot be visible. It will be visible on the upper side like this. So totally there will be 4 bars. Okay. At the supports 2 bars, and at the overhang, including overhangs, total number of bars will be 4 bars. So exactly if you look here, 4 bars are the supports including overall beam. But according to this condition, only supports required 4 bar, means you can keep like this also. So you can keep like this at supports here up to here, and again up to here, and again up to here, and again up to here. If you keep like that also aside to aside, for example in one row you will keep first 1 bar and again 1 bar like this. I will show here. 1 bar, 1 bar, 2 bars at the tension reinforcement, 1 bar, 1 bar, like this I am keeping. But from the side view, if you observe like this, you will visible only this front bars only. So if you keep short bars only at the support also, no problem. and you can keep one full length bar from here to here, like two bars, two full length bars from here to here. So these two bars you can keep full length also, no problem. But at the supports, minimum 4 bars will be required. At the supports, minimum 4 bars will be required. But if you keep here extra bar also, no problem. But for satisfying that condition, minimum at the support 4 bars will be required. Coming to the downside, at the middle span, minimum 3 bars will be required. Minimum 3 bars will be required. So you can keep one straight bar from here to here. So if you see here, there will be one bar already we keep like this, another bar will keep like this, and if I'll keep one more bar here, so if I will stretch this bar, so these are the straight bars. So if I'll keep this bar like this, sorry, this was with green color, already 2 bars provided, one more bar I will provide like this. So if you see here, 2 brown bars and 1 bar which was in green color, totally 3 bars. But what they are asking, 3 bars of 12 dia at the mid spans. So it will meet the requirements. So if you don't want like this, means you can keep in place of this just half of the bars like this, in the middle span just bar like this, like this, like this also you can keep. But somebody, what they will do means, one bar only they will crank both sides. For example, so this is one model, you can keep 3 full shade bars bottom and 4 full shade bars top row also, it will suits according to your condition. 4 bars of top, 4 bars here, 4 bars of 12 dia and 3 bars of 12 dia. But sometimes you can see the conditions, various ways you have to provide this reinforcement. I will show that one. Somebody will provide the bars like this. So this is one condition according to IS only, I am telling all these things. So the 2 bars will be provided, 2 bars aside by aside like this, and another 2 bars aside by aside like this. So minimum 3 bars will be required in the bottom side, we know that condition. So for that what they will do, they will keep 1 bar like this, they will provide entire 1 bar like this at the supports, and again they will crank here, and again they will provide to the mid spans here up to like this, and again at the exactly at the supports, again they will provide reinforcement, and again they will crank like this. So 1 bar only they will give crank like this. So if you observe clearly, what is the purpose, like the crank they are providing single bar means, if you observe, the reinforcement required 3 bars for the bottom side and 4 bars for the top side. If you bend 1 bar like this means, it covers 1 bar only, it covers top side and bottom side. So this is also one procedure. If you take some different textbooks, different types they are providing the beams, but the best option is what I am telling. If 4 bar means you can provide complete 4 bars top side, 3 bars means you can provide complete 3 bars bottom side. Otherwise you can provide minimum 2 bars completely top side, minimum 4 bars completely bottom side, and extra bars wherever it will be required as per the direction. For example, 3 bars will be required, the supports means you provide extra bar, and for that also there will be some calculations in the code book. It will be around, the bar length will be some 0.3 L, like that. So check the conditions once and you can provide according to the conditions. See here, this is the beam what I explained now. So see here, there will be 4 bars of 12 dia at this supports and 3 bars of 12 dia at the interior supports and the mid spans. So mid spans and 4 bars dia at the supports. See here how the bars will be provided. If you see here, 2 bars of 12. So if section, if you cut this section, what happens? So this top 2 bars will be this one, will be here, and bottom 2 bars will be this two. One will be here, 2 bars will be here. And again 2 bars will be required at the supports. So one bar, straight bar provided like this. So I will get with a different color, with yellow color. See here. So there will be one more bar from here to here, and here also here to here, and that bar they are provided here, that is third bar in the at the supports. And if you observe, there will be 2 bars in the bottom side also, and here this full bar will be cranks. So I will show with a different color. See here, it will comes like this, and again and again it will comes like this. Means they take one full bar and will crank like this, sorry, like this. If you see, the bar will be cranks like this here. Means they cover both top and bottom. Means if you see from side view, what it will be appear here and here. Means the bar will covers the here, and it covers the rear supports like this here. Means minimum 3 bars will be required top, bottom side. Means they cover with full 2 bars and 1 bar with mid spans, and the same bar will cover with tension interior supports. Like this they are providing crank also. So another bar they just keeping the half of the bar wherever it will be required. So this is the one procedure how they are providing the bars. And for cranking also, according to rule, be position standard rules like 0.3 times of L, here 0.15 times of L. So we have to follow these rules and conditions. Check once. Okay. Then so there will be some different types of the ways reinforcement detail of A, type A detailing, type B detailing, and C detailing also there. So all these are the based on the IS only. So already now I explained the same thing how it will provide in the beginning. Here if you see here, in the bottom reinforcement they provided some full 2 bars. In the hanger also they provided the, at the same time they just provided the cut bars in the bottom where they provide. In the middle span it will require 3 minutes, they provided the cut bars like this. Sometimes they are providing the crank bars, see like this. They are provided crank bars. Both it covers midspan and interior support. So these are the different ways of providing the bars to the continuous beams. Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.